So suppose we've already evaluated the integral from a to b of whatever this function is, and we've gotten some value out of that. Well, we know that the value is the area under the curve. So the area for this picture would be this, and so that's the area. And if I know the area from a to b under this curve, then I should easily be able to construct a rectangle that has a base length a to b. I guess I could sketch this a little bit better. That has a base length a to b, and find some height where these areas are equal to each other. So I can certainly easily construct such a rectangle. If I knew the area and I knew the base length, I could calculate the height. So I could write that the integral from a to b of this function, taking the antiderivative of the function f, I should be able to say, well, that's equal to the distance a minus b, or b minus a, excuse me, which is just a way to describe this distance, times h for that height. So if I did construct that rectangle and superimpose it across my graph, I would find that there is a point of intersection of that rectangle and my graph. Let's call this the f of c. Well, let's look at what we have here. Let me line this up a little better. I have a rectangle that I've constructed that I know is equal to the area under the curve. That part works. And I know the base of the rectangle is the same as the interval for calculating the area using the antiderivative. And now I can see that the height of the rectangle coincides with some f of c. So at this point, I can say that there exists some c value such that the f of c is the height of the area of a rectangle that is equal to the area under the curve. So I don't know what c is yet. I definitely don't know what f of c is, but I do have a way to describe the area under the curve using a rectangle that involves a point on my function. So I may be able to use my function to backtrack to whatever f of c is. This equality written here is the mean value theorem. And it says exactly what I just described, that for a curve on the interval a to b, the area calculated under the curve is equal to the area of a rectangle that has the same base, a to b, and the height of that rectangle must coincide with a point on the curve. And further, c must fall in the interval between a and b. So the mean value theorem gives us an existence of c and f of c. So now we look at the definition of the average value. And this says theorem, it's actually the AVD, the average value definition. So this f of c is defined as the average value. And the definition of the average value has a formula to find it, 1 over b minus a times the antiderivative, or the definite integral on the interval of f of x dx. All of this equals the f of c. All right, so right now we just have a bunch of cool things. We have a theorem, we have a definition, and we have some relationships that tie them together. But let's work at an example and kind of first use what we know to find the average value on a function, and then kind of play with it to see that in fact the relationships hold. So here I have a function, x cubed plus 2 times x minus 1 squared plus 1. And I want to evaluate this on the interval. It's hard to see right here what I'm, but we're looking at 0, which is obviously at the origin, to 1. So we want this area, and then we want to find f of c, or the average value for this function. So first let's start by just finding the area under the curve, because later I'm going to want to compare those. And we're looking on the interval from 0 to 1. So 0 to 1 of x cubed. Oh, before I do that, I definitely want to simplify this. I want to do my distributions and my expansions and combining like terms so I can have the easiest possible function for integrating. So this is times x squared minus 2x plus 1 plus 1, x cubed plus 2x squared minus 4x plus 2 plus 1 plus 3. Now let's integrate from 0 to 1, x cubed plus 2x squared minus 4x plus 3 dx. And that equals x to the 4th over 4 plus 2 times x cubed over 3 minus 4 times x squared over 2, so this is just a 2, plus 3x, which all still needs to be evaluated on the interval from 1 to 0. Well, when I put in zeros for all my x's, that's just going to be subtract 0, so all I have to do is plug in 1. So I have 1/4 plus 2/3 minus 2 plus 3, common denominator, 3 plus 8 minus 24 plus 36, all over 12. So my area then is 36 take away 24 is 12, plus 3 is 15, plus 8 is 23/12, which is approximately 1.9. Okay, so I know that the area under the curve, what I'm looking at is this area equals 1.9. So let's use the average value definition to find the average value, which is 1 over b minus a on the interval from a to b of my function. And I have all these values already for this particular function, so I can just plug them in directly to find the value for f of c. So f of c equals 1 over b minus a equals 1, b minus a equals 1, times the definite integral 1.9. So I know now that at y equals 1.9, or f of x equals 1, or f of c actually equals 1.9, I have a value for the height of my rectangle that has an area equal to the area under the curve. And if I sketch a little picture, I can say that the area under the curve on that interval is equal to the area of a rectangle from A to B with a height of 1.9. Well, the distance from A to B is 1. 1 times 1.9 is the area, 1.9. And so my two areas actually do match. And so I have my f of c. Could I find c from this? I could. I'm not going to. We'll just talk about it. How would I do that? Well, I know that the f of c equals 1.9. If I plug 1.9 in for my f of x, I would be able to find out which x's would give me the f of c equals 1.9. In this case, I have a cubic function, so I would expect 2 solutions. I think indeed I would end up with just, 3 solutions, or 3 possible solutions. I think I would actually end up with 2 solutions, because if I look closely at my graph, I can see that I have 2 places on this graph that have an f of c. I have f of c equals 1.9 and an f of d equals 1.9. So if I put these back in, I would be able to find C and D. I don't really want to do that. All I wanted was the average value for this function, so I am done.